Watch this fruit rot and collapse in on itself. This is our inescapable, everyday experience of physical reality. We live in a world where time seems to flow in one direction, from the past, through the present, and into a future that doesn't exist yet. But the two most successful scientific theories ever created fundamentally disagree on how a clock works. Quantum mechanics and general relativity offer two versions of time that are mathematically incompatible. This diagram shows the quantum view. Time is a rigid metronome ticking outside the universe at a constant, absolute pace. It provides the background stage for everything else, but nothing inside the universe can ever touch it or change it. When we try to combine these two systems, the foundation of modern science begins to fracture. Our understanding of reality rests on two definitions of existence that cannot both be right. Albert Einstein changed the rules with general relativity. He replaced the external clock with space-time, making time a malleable dimension that bends. This creates the block universe. In this model, every moment you've ever lived and every moment you ever will already exists as a static layer in a giant geometric block. The future is as real as the past. For most calculations, we keep these theories in separate boxes. But to understand the extreme, crushing physics of a black hole, or the very birth of our universe, we have to force them together into a single theory: quantum gravity. Merging a rigid external metronome with a flexible internal dimension creates a mathematical collision. The resulting paradox is the biggest hurdle in modern physics. In 1967, John Wheeler and Bryce DeWitt tried to mathematically unify these two rulebooks once and for all. They applied the rules of quantum mechanics to the entire geometry of space, attempting to find a single equation that could describe the state of the whole universe. The result was the Wheeler-DeWitt equation, but when they checked the math, the total energy of the universal wave function equaled zero. In the language of mathematics, the variable representing time simply dropped out of the equation. It didn't just slow down, it vanished. The first unified equation of the universe didn't just fail to explain the passage of time, it mathematically predicted a universe where nothing ever happens. This is the problem of time. When we attempt to marry two theories with such different definitions of the clock, the math locks up like these mismatched gears. The concept of evolution is destroyed by the contradictions in the rules. This frozen formalism suggests that at the most fundamental level, the universe is a static, timeless block. Our reality is locked in permanent stasis, with no room for beginning or end. If every moment is already fixed in place, it means the future is as unchangeable as the past. This realization deeply troubled Kurt Gödel and Albert Einstein, because it seems to leave no room for choice, or even the possibility of genuine change. If the Wheeler-DeWitt equation is accurate, our perception of a dynamic, changing world is a fundamental misunderstanding of the underlying math of the cosmos. This leaves us with a paradox. If the universe is fundamentally static, why do we see it changing? Why does the clock on your wall keep moving? The solution may be emergence. Time might not be a building block of reality, but an illusion created by how different parts of the universe interact with each other. The Page-Wooders mechanism relies on quantum entanglement. While this outer circle, the universe, remains frozen, these internal nodes link. Entangling an observer with a clock shares information. As the clock changes, the observer changes, creating a localized experience of time absent from the wider system. To a hypothetical outsider looking at the entire universe at once, nothing has actually moved. The total state is still zero. Time is a private, localized relationship between entangled systems. It's a bubble of experience, allowing us to feel movement within a fundamentally static reality. Another leading theory for this illusion is the thermal time hypothesis, which looks at how our human scale dictates what we see. Consider this single water molecule. At this scale, it doesn't have a temperature. Heat isn't a property that exists for one particle in isolation. Temperature only emerges when we zoom out to see billions of molecules colliding. It's a statistical average, a reality existing only for large groups. Time might work the same way. It doesn't exist for fundamental particles. Instead, it emerges as a byproduct of our limited, macroscopic human perspective. Our experience of a ticking clock is a consequence of our viewpoint. It is a persistent, vivid illusion, generated by our limited interaction with a fundamentally timeless cosmos.